this in and playing with it. But now I can't play with it until I can find the key. I need to have the key or I'm going to have to cut it off. After going through a whole bunch of keys to find the key that fits this safety lock, this is how we kept our kids from plugging it in and working this, because it is a very dangerous machine. We finally found the key. It takes that lock off.
Where? Where?
On my keyring. Many years ago I was living near a abandoned military warehouse, and inside they had these transformers still in the rafters that ran a fluorescent lighting system. Very archaic system indeed. So I managed to acquire a couple of these transformers. This one here is rated at, if I can get it in here and focused, it's rated at 60 cycles, 115 volts for input. Its volt amp or wattage is 400 watts, and its secondary voltage is 12,000 volts at an amperage of 60 milliamps. So this is a step-up transformer from house power to 12,000 volts. And I took it a few years ago and used it to make a Jacob's ladder for my kids to use for demonstration in school. Way back then. They're pretty well moved out by now. And as you can see, I wired in a house power cord, and it did have a lock through the end of the cord. That was to keep my kids from plugging it in and playing with it, because this is a very dangerous transformer. If anybody was to touch both ends of those insulators, it would definitely kill them. And that's why I had to keep this thing handled very carefully. On the switch I built here and hand wrote a on-off, that is just an ordinary power switch. Power goes through these red wires and hooks onto the back end of the transformer, directly underneath one of the output terminals. Then I have a wire from the output terminal that comes over to one side of the Jacob's ladder. On this side there is a jack, as you can see right there. That is a jack that was originally put there for the purpose of grounding the transformer with a ground wire. On this board I wasn't able to have any practical way to ground it, and I was, as you can see, using a 2-wire power cord instead of a 3-wire, so I haven't got this grounded. Anyway, the other output terminal, the red wire, comes out and down and hooks onto the Jacob's ladder, which is built onto a plastic board with a plastic tube holding the wires in place. These are fairly heavy, stiff wires. There's enough current sometimes, if I let it run too long, as you can see, it started to melt the insulation on that wire there. So I should not let it run too long. So now I shall plug it in and show how it works. Also, in wiring this up, I put in a idiot light to show when the power is on. When I made this many years ago, my children needed a project for their science classes. Every year one of them needed that. And so all 7 of my children used this Jacob's ladder in their demonstrations. And the tube is 18 inches high and a 4-inch diameter plastic tube. Frankly, if I had the material here and rebuilt this same transformer would be able to power a Jacob's ladder up to 5-6 feet high, easy. And now to show you how this works when it's turned on. That is what they call a Jacob's ladder. The spark originates at the bottom, builds up some ionized air. The ionized air is also hot, so it wants to rise up, so it carries the spark with it all the way up to the top. Eventually enough ionized air builds up inside the tube to where the spark gets even bigger and starts to pop out the top. And to show that that is a dangerous thing, it can light it.
Careful, you're loosen.
And now for what it looks like in the dark. TV.
Should have left it running for a little while.
I need to readjust it. And the thing is, if the bottom is too close together, let me see how it looks now. If it was too close together, it stays at the bottom. All right, try that again.